Hello friends, today I start with the next part in Ionic Equilibria. But before starting with that part, we just revise what we do in a last lecture. So in last lecture, we study the concept that is nothing but what is the meaning of Ionic Equilibria. Means what is the Ionic Equilibrium? That is the equilibrium between your ionized and unionized molecule in a solution. That is nothing but the ionic equilibrium. Then we study what is the type of electrolyte. So in that we studied what is the meaning of strong electrolyte and what is the meaning of weak electrolyte. Strong means what? That is completely dissociate. And weak means what? That is dissociate in a small extent. Then we studied that is whenever it is a weak electrolyte, so their dissociation you are showing by two-sided arrow, and whenever it is a strong electrolyte you show only one-sided arrow. Then what is the meaning of degree of dissociation? So degree of dissociation is what? That is number of mole dissociated divided by total number of a mole. Then we studied what is the meaning of acid base on the basis of three theories. So first theory is what? Arrhenius theory. So which explain the substance which can donate H plus ion in aqueous solution, that is nothing but your acid. And base is a substance which contain OH minus ion and produce that ion in aqueous solution, that is nothing but your base. Then we study the second theory which describe what is the meaning of acid and base. So first is Bronsted-Lowry's theory explain that acid means what? The substance which giving proton, means which donate the proton, and base is a substance which can accept the proton. Now this theory explain what is the conjugated acid base pair concept. Then the third theory which explain what is acid and base, and that explain on the basis of lone pair of an electron that can be accepted or donated. So according to them, Lewis acid means what? That can accept share an electron pair. Okay. And what is the base? Any species that can donate a share pair of electrons. Then we studied amphoteric nature of water. Means water can be behave as an acid or base depending upon the incoming substance. If incoming substance is basic, so water behave as an acidic in nature. Similarly, if incoming substance is acidic, so your water behave as a basic in nature. Then we studied what is the ionization of acid and bases. So your strong electrolyte, so how will it dissociate in a water? So the extent of dissociation is important. Similarly, where your weak acid and weak base, they are partially dissociating in water. So you are shown by the double-sided arrow. Then we studied the dissociation constant for weak acid and weak base. So dissociation constant for weak acid and weak base. So for weak acid you are shown by Ka. So that formula is very important for us. So Ka is nothing but what? Concentration of H plus ion into concentration of Am minus ion divided by concentration of your unionized acid molecule. Similarly, for dissociation constant for weak base is nothing but shown by Kb, which is equal to concentration of B plus into concentration of OH minus divided by concentration of your unionized base molecule, that is nothing but BOH. Then we studied what is Osford dilution law. And one thing is, remember, this law is applicable only for weak acid and weak base. So similarly, for this weak acid and weak base, Oswald dilution law gives in terms of degree of dissociation, there is a relationship between degree of dissociation and the dissociation constant for weak acid and their concentration term. So for weak acid, what is the relation? So alpha is equal to square root of Ka upon C, or alpha is equal to square root of Ka into V. Then Oswald dilution law for weak base, that is Kb is nothing but, so now in this case also they derive the relationship between degree of dissociation and your dissociation constant for weak base. So that is alpha is equal to square root of Kb into V, or alpha is equal to square root of Kb upon C. Then we start some autoionization of water. Autoionization of water means what? Your pure water have very less extent of ionization. Means what? They are not a strong electrolyte. So it doesn't dissociate into their H plus ion and OH minus ion. So your pure water are ionized to a very small extent. So in that case, we derive the Kw, that is nothing but ionic product of water, which is equal to 1 into 10 raised to minus 14. Now this Kw help us to derive the pH scale, and from that pH scale we can conclude which substance in their solution form are acidic, basic or neutral in nature. So now in this case your pH scale is from 1 to 14. So 1 to up to 6, that is nothing but acidic in nature. So for neutral that is 7, and for basic it is more than 7, means from 7 to 14. So for neutral solution, the pH is nothing but what? Negative log of H plus ion. So in that case, your H plus ion concentration for neutral solution is 1 into 10 raised to minus 7. For acidic solution, your H plus ion concentration is greater than 1 into 10 raised to minus 7. And for basic solution, your H plus ion concentration is less than 1 into 10 raised to minus 7. So whenever you have a concentration that is 1 into 10 raised to minus 7 for neutral solution, at that time your pH nothing but 7. For acidic solution, your concentration of H plus ion is greater than 1 into 10 raised to minus 7, means your pH is less than 7. And for basic solution, whenever your H plus ion concentration is less than 1 into 10 raised to minus 7, so at that time your pH is greater than 7. So this equation helps us to calculate the pH of your solution. Then we studied the hydrolysis of salt. So for that we describe what is the type of salt. So in that we studied the 4 types of salt. That is salt which is derived from strong acid and strong base. Second type, the salt which is derived from strong acid and weak base. Third salt, that is derived from weak acid and strong base. And fourth type is nothing but salt derived from weak acid and weak base. So in concept of hydrolysis, one thing is remember, that is in your water, the water is dissociated into H plus ion and OH minus ion. So whenever the concentration of both these ions are equal, so at that time your solution will be neutral. So if we take a first type of salt, that is the salt derived from strong acid and strong base, so that salt doesn't interact with your H plus ion and OH minus ion. So that's why your solution is a neutral. Similarly, when you take a salt that is derived from strong acid and weak base, so at that time only the basic salt, see in this case it is derived from weak base. So what happened? The salt of strong acid and weak base, showing the solution is acidic in nature. Okay. Then third type of salt, that is nothing but salt of a weak acid and strong base. So at that time your solution will be basic in nature. And fourth type of salt, that is a salt of weak acid and weak. Now fourth type of salt, that is your weak acid and weak base. So that is the solution may be your acidic, basic or neutral depending upon the salt which is formed from weak acid and weak base, their Ka and Kb value. If that salt is made up of such a weak acid and weak base, in that case Ka is greater than Kb, then your solution will be acidic. If your Ka is less than Kb, so at that time your solution will be basic. And if Ka is equal to Kb, so at that time your solution will be neutral. Then we studied the buffer solution. What is the meaning of buffer solution? So buffer solution means a solution which resists the drastic change in a pH when a small amount of strong acid or strong base or water is added to it. So in that case we studied two types of buffer, that is acidic buffer solution and basic buffer solution. So for acidic buffer solution, your requirement is you require weak acid and its salt with a strong base. And for basic buffer, you require weak base and its salt with a strong acid. So where we apply buffer solution? So in biochemical biochemical system, in agriculture, in industry, medicine, and in analytical chemistry. Then we start with a solubility equilibria. Means what? So now for solubility equilibria, we take a sparingly soluble salt. Means what? AgCl. We take an example of AgCl in that. So AgCl, when you put in a water and stir vigorously, so what happens? A very small amount of AgCl will dissolve in a water and it forms a saturated solution. But most of the salt remain undissolved form. So now in this case your solid AgCl is in contact with your saturated solution. So AgCl is your strong electrolyte. So what happens? AgCl is dissolved in a water and it dissociates completely into its constituent ion, that is Ag plus and Cl minus. So now there is an equilibrium. Equilibrium between what? Between your solid AgCl and your dissolved ion, that is Ag plus and Cl minus ion. So this equilibrium is called solubility equilibrium. So for solubility equilibrium, it is important that you take a sparingly soluble salt, and that sparingly soluble salt must be in equilibrium with its ion. So now AgCl gives you Ag plus and plus Cl minus. So there is an equilibrium between your unionized AgCl solid and their constituent ion, that is Ag plus plus Cl minus. So in this case, what is our equilibrium constant? So K is equal to Ag plus into Cl minus upon AgCl concentration. So AgCl concentration we taken as K dash. So now we derive a new constant, that is solubility product, that is Ksp. So Ksp is equal to concentration of Ag plus into Cl minus ion. So one thing is, remember, for solubility product, what is our definition? In saturated solution of a sparingly soluble salt, the product of equilibrium concentration of the constituent ion raised to the power equal to the respective coefficient in a balanced equilibrium expression at a given temperature is called solubility product. means Ksp is equal to, if we consider any general sparingly soluble salt, that is Bxay, so in that case x times b raised to y plus, that is the valency, plus y into a raised to x minus valency, means Ksp is equal to concentration of b raised to x times and a minus raised to y times. So this can be explained by taking example of any salt, that is sparingly soluble salt. That is, we take SCAF2. Now CF2 dissociate as Ca2 plus 2F minus. So now in this case Ksp is equal to Ca raised to 1, because coefficient of calcium is 1 and fluoride raised to 2, means because coefficient of fluoride is 2. Similarly, we take another example of sparingly soluble salt, that is Bi2S3. So 2 times Bi3 plus 3 times S2 minus. So in this case x is equal to 2 and y is equal to 3. So Ksp is equal to Bi 3 plus raised to 2 and S2 minus raised to 3, because x and y in this example is 2 and 3 respectively. So today now we start with the next concept, that is we have to derive relationship between solubility and solubility product. Means we have derived a relationship between S, that is solubility, and that is Ksp, that is nothing but our solubility product. So solubility product. Now and solubility product. So first of all, what is the meaning of solubility here? So solubility is what? So solubility of a compound is an amount in a gram that dissolve per unit volume. Means your compound must be in a gram and that may be dissolved in per unit volume. So which may be 100 ml or 1 liter of its saturated solution. Now what is the meaning of molar solubility? Now molar solubility is nothing but the number of mole of the compound that dissolved to give 1 liter of a saturated solution. It's called its molar solubility. So the molar solubility means what? The number of a mole of a compound that dissolved to give 1 liter of a saturated solution. So molar solubility is what? Solubility in gram per liter upon molar solubility in gram per mole. So for this we consider the general example, that is Bxay. So what is the solubility equilibrium for this general salt, that is a sparingly soluble salt, Bxay? So Bxay gives you x times b raised to y plus y times a raised to x minus. So solubility product for this equation is what? So Ksp is equal to concentration of b raised to x times and a raised to y times. Now for this ions, our molar solubility is what? So we consider S, capital S is the molar solubility of a compound. So equilibrium concentration of ion in a saturated solution will be given as concentration of B, which is equal to X times S mole per liter, and concentration of A, that is your anion, which is equal to Y times S mole per liter. Now then how will you represent our Ksp for this? So Ksp is equal to X times S raised to X into Y into S raised to Y. So in this concentration, in place of concentration of B y plus, we write X times S, okay, and in place of your concentration of anion, we write Y times S, okay. So Ksp in this case is given as, in concentration bracket, we write X times S raised to X into Y times S raised to Y. So which is nothing but X raised to X into Y raised to Y into S raised to X plus Y. So this is our elucidation, that we consider the concentration in terms of solubility, molar solubility. So in this slide, molar solubility definition is very important for us. So once again we revise, what is molar solubility? The number of mole of a compound that dissolve to gives you 1 liter of a saturated solution. It's called its molar solubility. So in this expression, we derive the relationship. Try to derive the relationship between your Ksp and your S. Now we go to the next part. That is, we continue with this. So we consider the example for this. So we take first example, that is AgBr. So AgBr, that sparingly soluble salt, dissociate and gives you Ag plus Br minus. So X is equal to 1 and Y is equal to 1. So Ksp is given as what? That is X raised to S, X into Y raised to Y into S raised to X plus Y. So Ksp is given as what? S into S, that is S square. Now we consider the next example, that is for PbI2. So PbI2 is dissociate into Pb2 plus 2 times I minus. So X is equal to 1 and Y is equal to 2. As we know, what is the relationship between solubility and solubility product? Our formula is what? Ksp is equal to X raised to X into Y raised to Y into S raised to X plus Y. Now X is 1, Y is 1. So how will you conclude the relationship? That is Ksp is equal to 1 raised to 1, 2 raised to 2 and S raised to 1 plus 2. So that is nothing but 4S cube. Now we start with the third example, that is AlOH thrice. So AlOH thrice dissociate into what? AlOH thrice is dissociate into Al3 plus 3 times OH minus. Now X is equal to what here? 1 and Y is equal to 3. So Ksp is equal to what? 1 raised to 1, 3 raised to 3, S raised to 1 plus 3. So that is nothing but your answer will be 27 S raised to 4. So in this way, in your exam also, they may ask you to find out the solubility product for the given salt. At that time, your first requirement is what? You have to write the dissociation of your sparingly soluble salt. Then you have to identify what is your X and what is your Y. Then as you know, Ksp is equal to what? X raised to X, Y raised to Y into S raised to X plus Y. So we now clear what is the relationship between your solubility and solubility product. If you want to try at your home, so try some other example also. So you try for Ag2CrO4 means silver chromate. Then you try for calcium phosphate, that is Ca3PO4 twice. Then you try for chromium hydroxide as well. So you can solve and try this example in your home. Now next we start with the condition of precipitation. Means if you carried out any reaction, so which reaction gives you precipitation type of reaction or precipitate? So what is the condition for precipitation? So that we see in this slide. So first of all, for this you must know what is the ionic product. So ionic product of an electrolyte is defined as in the same way as your solubility product. Means as you describe the solubility product, similarly you can describe for ionic product also. But what is the difference between ionic product and solubility product? That we have to see here. So the only difference is that ionic product expression contain concentration of ion under any condition, whereas expression of KSP contain only equilibrium concentration. Means requirement is what? Your ionic product can gives you the expression of your ionic product of a concentration of ion at any condition. Means that is not a requirement that equilibrium must be established between your ionized and unionized form. But your ionic product can explain the relationship that is your ionic product of your concentration of ion under any condition, whereas your KSP only gives expression at equilibrium concentration. So there are three situations. So when you get a precipitate, and when you get a saturated, and when you get a unsaturated form of solution. So first of all, here if ionic product is equal to solubility product, so at that time you said the solution is saturated and solubility equilibrium exists between them. This is your first condition when your ionic product is equal to your solubility product. Now then only your solution is saturated and solubility equilibrium exists between them. If your ionic product is greater than solubility product, so at that time your solution is supersaturated and hence precipitation of compound will occur. Third one is your ionic product is less than solubility product. So at that time your solution will be unsaturated and precipitation will not occur. See, in this three form of solution, first of all you know what is the meaning of unsaturated, what is the meaning of saturated, and what is the meaning of supersaturated. So first of all, whenever you said unsaturated, means what? Now your solution is made up of solute and solvent. So unsaturated means what? Now solvent have an ability to dissolve more amount of solute, still it dissolve less amount of solute in that. Means if you add more than that amount of solute also, still it can dissolve, but you can't dissolve more amount of solute, you just add some amount of solute, then you said it is unsaturated. Means its ability to dissolve more amount of solute, still it dissolve less amount of solute in that. So that is the meaning of unsaturated. Saturated means what? Now at a particular temperature, okay, your solvent capacity is over to dissolve that particular solute. So if you add more amount of solute after that ability, so you get a solid which is left at the bottom of your solvent. So before that condition, your solution must be saturated. Now what is the meaning of supersaturated? See, the tendency of solvent to dissolve any solute is depend upon the temperature. If you increase the temperature, then its ability maybe increases to dissolve that particular solute. So whenever you take any hot saturated solution, okay, means you add a excessive amount of solute in that and you increase the ability of solvent to dissolve the solute in that, and then you cool that hot saturated solution. So as the temperature decreases, the excess of solute now left or that can be appear on the wall of your container, means that is a supersaturated. So now in this way you know what is the meaning of saturated, supersaturated and unsaturated. So whenever your ionic product is equal to your solubility product, at that time your solution will be saturated and solubility equilibrium exists. Whenever your ionic product is greater than your solubility product, at that time your solution will be supersaturated and hence the precipitation of the compound will be occur. Similarly, when ionic product is less than solubility product, the solution will be unsaturated and precipitation will not occur. So see, this criteria is very important when you have to decide in which reaction your solution will be precipitated or in which reaction your solution will be saturated or unsaturated. So that can be determined if you know what is the ionic product and what is the solubility product for the reaction. Now next we start with a common ion effect. Now common ion effect means what? Now as the word suggests you, common ion means what? In the species you have a common ion in that. So for common ion effect, we consider the example that is our weak acid and its soluble ionic salt, that is a sodium acetate. Now if you recollect, in our buffer type we studied the first, that is acidic buffer. For that we take a weak acid and its salt with a strong base. That same example we take to explain what is common ion effect. Now consider a solution of a weak acid, that is acetic acid, and your soluble ionic salt, that is sodium acetate. Now next what we do, we take, as you know, acetic acid is a weak acid, so it dissociates only slightly in a solution. So you represented what? That is acetic acid reversibly gives you acetate ion plus H plus ion. Now next is your sodium acetate. So as sodium acetate is known to us, that is it is a strong electrolyte. It dissociates completely, then completely in a solution. So that's why sodium acetate gives you acetate ion plus Na plus. Now both the acid and salt, if you see both the reaction, in both the reaction they produce acetate ion in a solution. One thing is, remember, in this case sodium acetate dissociate completely and it provides you the acetate ion. Okay. So now according to Le-Chatelier principle. So Le-Chatelier principle means what? If you increase a concentration of one of the ion, so at that time that must be used up. in the reaction. Then only your reaction must be balanced. Okay. So now what happened? In this case, the addition of your acetate ion from sodium acetate to the solution of acetic acid. So what happened? It shifts the equilibrium. Okay, that is dissociation of your acetic acid to the left. Okay, thus the reverse reaction is a favor. Means the as the concentration of your acetate ion is more, which combine with H plus ion to form unionized acetic acid. So in this way, what happens? Your acetic acid dissociation will be suppressed due to the presence of sodium acetate and which containing the common ion, that is acetate ion. So now what do you mean about common ion effect? So see, if you want to define common ion effect, so how will you define with the help of this example? See what we do in this example, we take acetic acid, that is weak electrolyte, and we take its salt with a strong base, that is nothing but sodium acetate. Now what happened? In both the reaction you get a acetate ion. So now when you add sodium acetate in acetic acid, so at that time you get a more concentration of your acetate ion. So according to Le-Chatelier principle, the acetate ion which form in which have a large concentration in a solution, that can be balanced by use up with this acetate ion. So acetate ion react with H plus ion. So once again you get a acetic acid. So in this case you can suppress the dissociation of your acetic acid. So now what is the definition of your common ion effect? Means how will you define or how will you recollect that from this summary? So common ion effect stated that the ionization of your weak electrolyte is suppressed in presence of strong electrolyte containing an ion common to the weak electrolyte. So in this case, for explain common ion effect, what is the weak electrolyte we are taken? That is acetic acid. Okay, and its dissociation is suppressed by addition of your strong electrolyte, that is nothing but in this case we add sodium acetate. Okay, and in both these ion we have acetate ion which is common to both of them. Okay, and in this way your acetic acid dissociation can be suppressed. Okay, so common ion effect is a special case of your Le-Chatelier principle, in which stress is applied to the equilibrium system is an increase in a concentration of one of the product. The effect of this stress is reduced by shifting the equilibrium to the reactant side. See, as we know, as we studied in 11th standard, what is the Le-Chatelier principle? So in that case also, if we increase the concentration of one of the ion, we can balance by use up that ions. Okay, so this common ion effect is a special case, okay, of what? Our Le-Chatelier principle. Means if we apply stress to an equilibrium system is an increase in a concentration of one of the product, so the effect of this stress is reduced by shifting the equilibrium to the reactant side. Okay, now next, as you know, the hardness of water. Hardness of water is due to what? Calcium of ion. Means Ca2 plus ion whenever present in your water, so it gives the hardness to the water. So how will you remove that calcium ion? Okay, to remove the hardness of ion. So what we do? The OH ion of that calcium ion in water, in lime water, is in the form of a lime, that is CaOH twice. Okay, means whenever you have a hard water, so in that case calcium ion is present in a CaOH twice form. That OH minus ion of a lime react with a HCO3 minus ion present in a hard water to form CO3 2 minus ion. Now that OH minus ion plus HCO3 minus gives you CO3 2 minus plus H2O. So the solubility product of calcium carbonate is very low, and the addition of lime make ionic product is more than your solubility product, which result in a precipitation of calcium carbonate, thereby removal of a hardness of water. Means to remove the hardness of water, it is necessary to react your hard water with a bicarbonate. Okay, and in this way your ionic product will be greater than solubility product, and which result in precipitation of calcium carbonate and thereby removal of your hardness of water. Now we start with the common ion effect and its stability. The presence of common ion effect affect the solubility of sparingly soluble salt. So for this explanation, we take example of sparingly soluble salt, that is AgCl. So AgCl gives you Ag plus and Cl minus. Now to explain the presence of common ion effect affect the solubility, that we are explained by taking example of a sparingly soluble salt. That is nothing but AgCl. AgCl gives you Ag plus plus Cl minus. So now what is the solubility product for AgCl? So AgCl. So Ksp, in this case your X will be 1, Y is equal to 1. So Ksp is equal to concentration of Ag plus ion into concentration of your Cl minus ion. Now what we do, in this saturated solution we add silver nitrate. Okay, silver nitrate we are added in saturated solution of AgCl. So what happened, as your silver nitrate is a strong electrolyte, it gives you AgNO3 gives you Ag plus plus NO3 minus. So now see, as you know, common ion effect means what? The common ion must be containing by your weak electrolyte and your strong electrolyte. So in this case Ag plus ion is a common. So the dissociation of AgCl and AgNO3 produces common silver ion. So the concentration of silver ion in a solution is now increasing. Okay, due to the complete dissociation of your silver nitrate ion. So according to Le-Chatelier principle, once again stress is produced as the concentration of Ag plus ion increases. So you can reduce the stress by using the excess ion which is formed in a solution. So in this case silver ion formed in a large concentration. So according to Le-Chatelier principle, the addition of Ag plus ion from silver nitrate to the solution of AgCl shift the solubility equilibrium of AgCl from right to left. Now in this case you form Ag plus ion which is in a more amount. So that's why in AgCl dissociation you get Ag plus and Cl minus. So Ag plus concentration is more, so that can be used up by Cl minus. So once again you get AgCl. So in this way you can change here you can shift your solubility equilibrium of AgCl from right to left. Okay, means toward your reactant side. So the reverse reaction in which AgCl is precipitated is favor until the solubility equilibrium is re-established. So the value of your Ksp, however, remain the same since it is an equilibrium constant. The solubility of sparingly soluble compound decreases with the presence of common ion effect. Means as you know, what is the common ion effect? It suppresses the solubility of your weak electrolyte by addition of strong electrolyte. So in this case also, we add silver nitrate in silver chloride. So what happened? The solubility of your sparingly soluble salt will now decreases due to the what? Due to the presence of a common ion solutions. Okay. So we just revise what is common ion effect and its solubility stability. So in this case we take example of silver chloride, which is dissociate to gives you silver plus and Cl minus ion. Now for this we add silver nitrate. So we increase the concentration of silver ion. So silver ion concentration is more. So according to Le-Chatelier principle, we have to reduce the stress by using that silver ion which is formed in a excess. And that's why we once again get AgCl, means we shift the equilibrium from right to left. Means due to the common ion effect, we can decrease the solubility of a sparingly soluble salt. Okay. So in this way, we complete our common ion effect and its stability. Now we start with the problems in this chapter. But we just first of all study which are the formula that is important to solve this problem. Okay. So we start with the problem. So first of all we start with the formula for that. So important formula and concept we just cover in this chapter. So first formula of R, that is degree of dissociation. So degree of dissociation is shown by alpha, which is equal to number of mole dissociated divided by total number of moles. Okay. So what is percentage dissociation? Which is equal to alpha into 100. So first of all, first formula is degree of dissociation, which is equal to number of mole dissociated upon total number of mole, and percentage dissociation is equal to alpha into 100. Then our second formula, that is dissociation constant of weak acid, which is shown by Ka. So Ka is equal to concentration of H plus into concentration of A minus upon concentration of undissociated acid molecule. Now third formula, that is dissociation constant of a weak base, that is Kb, which is equal to concentration of B plus into concentration of OH minus upon concentration of undissociated base molecule. Then the fourth, that is at equilibrium, we have to consider the fraction dissociated will be alpha and fraction that remain undissociated will be 1 minus alpha. So amount present at equilibrium per mole, which is equal to alpha, and concentration at equilibrium per mole DMQ, which is equal to alpha upon V. So amount present at equilibrium per mole is equal to 1 minus alpha, and concentration at equilibrium per mole per DMQ, which is equal to 1 minus alpha upon V. See, the concentration, that is a fraction that dissociate, that will be alpha at equilibrium, and that will be undissociate will be 1 minus alpha. So that alpha, that is nothing but your amount, and its concentration is nothing but alpha by V. Similarly, the undissociate at equilibrium will be 1 minus alpha, and the concentration of undissociate at equilibrium will be 1 minus alpha upon V. Now continue. That is, then what is the relationship between your degree of dissociation and your dissociation constant? First we consider for acid, then we consider for weak base, means weak acid and weak base. So for weak acid, that is K is equal to alpha square upon 1 minus alpha into V, which is equal to alpha square C upon 1 minus alpha. Now for weak acid, HA, so alpha is very small, so at that time 1 minus alpha is nearly equal to 1. So your Ka will be, Ka is equal to alpha square upon V, and Ka is equal to alpha square C. So now alpha is equal to what? Square root of Ka upon C, or alpha is equal to square root of Ka into V. Now we consider for weak base, that is Kb. So Kb is equal to what? Alpha square upon 1 minus alpha into V, which is equal to alpha square C upon 1 minus alpha. So Kb, now that is for weak base. So for BOH, alpha is also very small. So 1 minus alpha is nearly equal to 1. So Kb is equal to alpha square V upon V, and Kb is equal to alpha square C, and alpha is equal to what? Square root of Kb upon C, or alpha is equal to square root of Kb into V. Now the equilibrium constant for ionization of water, that is K, which is equal to concentration of H3O plus into concentration of OH minus upon H2O square, that is K into H2O square, which is equal to H3O plus into OH minus. So in this case your Kw is what? H3O plus concentration into OH minus concentration. That is Kw is nothing but K into K dash. That is the ionic product of your water. Now one thing is, remember, next formula is what? Concentration of your H3O plus into concentration of OH minus ion, which is equal to 1 into 10 raised to minus 14. Then next formula is pH is equal to negative log of your H plus ion concentration. pOH is what? Negative log of log to the base 10 OH minus ion concentration. Then next is pH plus pOH, which is equal to 14. Then pH of your acidic buffer, that is pH is equal to pKa plus log to the base 10 concentration of salt upon concentration of acid. Now pK is what? Negative log to the base 10 dissociation constant of acid, that is nothing but Ke. Then pH of basic buffer, which is equal to pH is equal to pKb plus log to the base 10 salt upon base. So pKb is what? Negative log to the base 10 Kb. Now solubility product. Solubility product Sp is equal to what? Concentration of your cation raised to its coefficient into concentration of anion, which is raised to its coefficient. Now molar solubility is what? Solubility in gram per liter upon molar mass in gram per mole. Now the relationship between your solubility and solubility product is given as Ksp is equal to x times s raised to x into y times s raised to y, which is equal to x raised to x into y raised to y into s raised to x plus y. So in this way we complete our formulas that is in this chapter. Okay. Now we try to solve problem on the basis of these formulas. So first we start with the problem number 1, that is a weak monobasic acid. Okay, is 0.05% dissociate in 0.02 molar solution. Calculate dissociation constant of acid. Now what you have to find here? Ka. Ka you have to find here. And what is the data they given you? That we have to know. That is the first given you 0.05% dissociate means in 0.02 molar solution. So dissociation constant of acid is given by Ka is equal to alpha square into C. Hence percentage dissociation is what? Alpha into 100. Now alpha is what? Percentage dissociation upon 100. Now as you know, in this problem they give 0.05% dissociation. Means they gives you the percentage dissociation. It doesn't gives you degree of dissociation. So alpha is equal to what? 0.05 upon 100, which is equal to 5 into 10 raised to minus 4. Then next is what? Concentration in 0.02 molar solution. So C is equal to 0.02 molar means which is equal to 2 into 10 raised to minus 2 molar. So now we have to put alpha and C in our formulas, that is Ka is equal to alpha square C. So Ka is equal to 5 into 10 raised to minus 4 the whole square into 2 into 10 raised to minus 2. So 5 square is 25, 10 raised to minus 4 square is 10 raised to minus 8 into 2 into 10 raised to minus 2. So 25 2s are 50. So 50 into 10 raised to minus 10. So Ka is equal to 5 into 10 raised to minus 9. So as you know, in this sum we are using, that is dissociation constant, which is equal to alpha square C. So alpha is directly doesn't give given in a sum, but they gives you percentage dissociation. So you have to first of all calculate degree of dissociation, then C, that is you know, and then you have to just put all this value in your formula, then you get the answer for your dissociation constant of acid, that is Ka. Now we start with the second problem. The problem is the dissociation constant is given to you, that is dissociation constant of NH4OH is 1.8 into 10 raised to minus 5. Calculate degree of dissociation in 0.01 molar solution. Now as you know, the degree of dissociation, this is the base, NH4OH is a weak base. So alpha is equal to square root of Kb upon C. Now Kb is given to you, that is 1.8 into 10 raised to minus 5, and C is given to you, that is 0.01 molar. So that is nothing but 1 into 10 raised to minus 2 molar. So you have to put this value in your above formula. So alpha is equal to square root of 1.8 into 10 raised to minus 5 upon 1 into 10 raised to minus 2. So as you know, square root of 1.8 into 10 raised to minus 3. Now 10 raised to minus 3 square is not possible, square root is not possible for us. So what we do? We just shift our decimal. So in our next line, square root of 18 into 10 raised to minus 4. So now see, 10 raised to minus 4 square root, that you know, that is 10 raised to minus 2. Now 18. So you have to find in your logbook what is the square root of 18. Okay. So 18, if you see it is nearer to 16, means your answer is nearer to 4. So your answer is 4.242 into 10 raised to minus 2. So you have to shift the decimal on the left hand side. So your alpha become 0.04242. So in this problem, they given you the dissociation constant for weak base and the concentration is given to you. Then you have to find the degree of dissociation. Okay. So next problem we see in our next lecture.